Okay, in this video we're going to look at special angles. Now the special angles are angles whose trigonometric ratios can be found exactly. So these are angles whose values of further trigonometric ratios can be found exactly. We're going to focus on the angles in the first quadrant, which are 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Then all other angles in other quadrants whose reference angles are 30, 45 or 60 will be special angles as well. Okay, so we're going to start with 30 and 60. To prove this one, we're going to consider an equilateral triangle of side 2. So suppose this is an equilateral triangle and each of the sides is of length 2. So this is length 2, and the base is of length 2 as well. What I want to do is we are going to divide it in half. So let's call this one H. So that means this is going to be 60 degrees here, 60 degrees here, and then this one is going to be 30 degrees. Now, if we just consider this half of a triangle, then we can use Pythagoras to find H, because this is going to be of length 1. So that means, according to Pythagoras, H squared plus 1 squared is going to be 2 squared. So H squared is going to be 4 minus 1. So that means H is going to be plus or minus square root 3. But since it's a distance, it means H is just square root 3. So I'm going to go in here and say H is equal to square root 3. Right, with that we can now write all the values of sine, cosine of 60 and 30. So let's start with 60 here. So that means sine 60 is going to be opposite, which is square root 3 of hypotenuse, which is 2. And cosine 60 is going to be adjacent, which is 1, over hypotenuse, which is 2. And then tangent 60 is going to be square root 3 over 1. Okay, then we can now do the one for 30. So sine 30 is going to be the opposite, which is 1 over 2. And then cosine 30 adjacent is going to be H, which is square root 3. And then tangent 30 is 1 over root 3. you're going to notice that the sine of 30 is equal to the cosine of 60, and the sine of 60 is equal to the cosine of 30. This is because of a property of angles that add up to 90, because 30 and 60 add up to 90. Then the sine of the one is equal to the cosine of the other. In fact, in general, the cosine of theta is going to be always equal to the sine of 90 minus theta, and vice versa. Right, so that's the trigonometric ratios of 30 and 60. We're now going to go to 45. For 45, we're going to consider an isosceles right triangle. So if this is equal to 1 and this equals to 1, so that means that's isosceles. So this angle is going to be 45 here. And then by Pythagoras, the hypotenuse is going to be square root 2. So that means the sine of 45 is going to be equal to 1 over root 2, and this we can either write it like this, or we can write it like that. Cosine of 45 again is going to be 1 over root 2 because of the symmetry of this triangle. Then tangent 45 is going to be equal to 1. Okay, so we have covered 30, 45, 60. I'm now going to cover 0 and 90, and then we'll extend this to the other quadrants. Okay, so let's start with 0. So if you imagine we have a triangle here, and if you imagine that this side is collapsible, so this is theta here, this is x, this is r, and this is y. Okay, so sine theta is y over r. Maybe let me write this here. Sine theta is y over r. Cosine theta is x over r. I just do sine and cosine. Tangent follows immediately. So if this thing is collapsible, we're going to start with y there, and then maybe y now is there, then y now is there, and then y now is there, and then so what we notice is that as the angle theta becomes closer and closer to 0, the first thing is that of course y is going to 0. So this opposite is becoming shorter and shorter and shorter. But the other thing that we're noticing is that this this hypotenuse side is becoming more and more like x. Okay, so the opposite, the adjacent and the hypotenuse are becoming more and more like equal to each other. So r is becoming more and more equal to x. So what's going to happen here is that as theta goes to 0, so that means sine 0 is going to be 0, because we said y is going to 0. It's going to be 0 over r, which is 0. And then cosine 0, we said r is becoming more and more like x. So it's going to be like x over x, so that is going to be equal to 1. So that means we've established that cosine 0 is 1 and sine 0 is equal to 0. Right, we're now going to look at the case of 90 degrees. So starting again with this right angle triangle, we are this time going to assume that the horizontal side here is collapsible. So we're going to start, so again this is our y, this is our x. So if it's collapsible, then that edge of or vertex of the triangle is just going to start sliding this way. So this is what things are gonna it's gonna look like. So your theta is becoming bigger and bigger, approaching 90. Okay, so as this point gets closer and closer here, you can see that x is going to so as theta goes to 90, x is approaching 0. Okay, and then as this thing gets closer and closer here, you can see that y, which is the opposite, and the hypotenuse are becoming more and more equal. So if we go to this, y is becoming more like r, so that means sine 90, because these two are becoming more and more like each other, so that's going to give us 1. And then cosine 90 on the other hand, x is becoming 0, so that's going to be 0, so that is going to be 0 there. So that covers all of them, the ones in the first quadrant. So let's just do a review of what we have. I'm going to write theta in degrees here, theta in radians. I'm going to write sine theta here and cosine theta. So 0, 30, 45, 60, then 90. Then the next one in the second quadrant is going to be 180 minus 60. That's going to be an angle with the same reference as this one. So that's going to be 120 there. We're just going to end there because of our space. In radians, this is still 0. That's pi over 6, pi over 4, pi over 3, pi over 2. This is 2 pi over 3. Sine 0 is 0, sine 30 is 1/2. And this one is root 2 over 2. And this is root 3 over 2. This is 1. This is going to be root 3 over 2. Cosine 0 is 1. Cosine 30 is root 3 over 2. Cosine 45 is the same as sine 45. Going to be 1/2, 0 here. And then this one is going to be -1/2. And then all other angles which have got 30, 45, 60 or 90 as a reference will be special angles. So in the first quadrant we have got 45, and then we have got 30, we have got 60 there. 90 is also special. Then in the second quadrant, the one in the middle is going to be 135. This is going to be 120. It's going to be 150. The third quadrant, the one in the middle is going to be 225. 210 here. 240 there. 270 is also special. Then the one in the middle here is 315. Then we have got 330 here and 300 here. So all these and their corresponding coterminal relatives are going to be special angles. Just before we finish this video, I'm just going to bring to your attention a very interesting sequence here. If you look at these numbers here, so let me just write them down here. So you have got, so if we just look at the sine of theta, got 0, 30, 45, 60 and 90. So here it's 0, then 1/2 here, root 2 over 2, root 3 over 2, and sorry, it's 0 here. These, if you like, you can write them as so we can see that all of them are over 2. This one is the same as square root 1 over 2. Then here you've got square root 2 over 2, square root 3 over 2, and this one is square root 4 over 2. And of course here you've got square root 0 over 2. And then of course the cosine values do at the exact opposite. They start at 1 and go down to 0. Okay, so the special angle is for us.